So welcome everybody to the Nordic Joint Nordic and Swedish Astrobiology Network meeting. It really arose out of the need of having some kind of science associated with the SWAN meeting. SWAN means Swedish Astrobiology Network. It has existed for 6 years now, and it has only held business meetings. There's no real science actually involved. So this was the starting point. On the other hand, since I was happy to host this year, and being from Nordida, which has immediately a Nordic perspective, it is mandatory and important, of course, that this meeting is having a scope also towards the other Nordic countries. And that's why we have at least a few of us from outside Sweden and the other Nordic countries. So that's as far as this particular setup of the meeting is concerned. I don't think there are immediate plans for the next meeting, except that there is a next SWAN meeting being held in Uppsala in March, as was just discussed at the business meeting here. And so this may be another possible place where we could have science talks and an update on the progress of Swedish astrobiology. Let me also make another remark here. Nordida had organized a few astrobiology meetings in the past. In the year 2004 we had 2 meetings, and in the year 2005 we had 2 meetings, and then we had a winter school in 2006. In connection with those meetings, we had a single special edition in the International Journal of Astrobiology. And the editor of this is he's Simon Mitten. He's happy to host again guest editors for the occasion of this meeting, or perhaps at least this meeting as one starting point, but we could indeed have contributions from also people that have not been participating at this particular meeting. So this is first of all, I think, a very interesting possibility that we could be forcing ourselves into writing astrobiology articles. These would be original research. They would not be, but they could also be, to some extent, review-like. But of course they would be not just, of course, repetitions of other published work. So I invite therefore everybody to contact me as soon as possible during the break, for example, and I will also ask you whether you would be happy to provide material for a special edition. This last time it was extremely swift. Actually, we had the papers were published just a few months after the final articles came in. All these articles will, of course, be peer reviewed. So I think with these remarks, I mean, also, of course, I guess everybody knows that we have enhanced activity here in the Stockholm region astrobiology because of the astrobiology graduate school, which involves 8 students. And so with this, of course, we have a lot of activity and a significant amount of audience. We used to have these meetings and seminars every second Friday, certainly until the summer. And now we had a few such meetings also in the fall, and we'll have more in the spring again. So that is another aspect. And then finally, let me also say that Nordida has various deadlines coming up. Some of them may be of interest to you. So the first deadline is the one for project applications. Projects are activities which last for something like between 1 month or sometimes could be 2 months. And this would be activity at the institute. Scientists would be invited. They can also apply, and if accepted, can participate here. They would, in most of the cases, come from either outside Stockholm or elsewhere in the Nordic countries, and certainly also from elsewhere in the world. Up to something like 20, typically, absolute maximum would be 24 researchers at any one time. And so Nordea had one such program already in the fall last year, and it will have four more programs coming up this year. The first one is actually on homochorality, and that is obviously related to astrobiology. The work of that particular program is also most likely to be published in a special issue of the Origins of Life and Evolution of the Biosphere, where Alan Schwartz is the main editor, and so we have been in touch with them. So I think this would be helpful, all of these activities, and not just enhancing the research in astrobiology among ourselves, but also elsewhere in the Nordic countries. So I give now the word to Lennart Nord, who is from the Swedish Space Board, and he will be talking about astrobiology-related work that comes to his mind from a Space Board perspective. Lennart, please.
Okay, thank you, Axel, for inviting me to say a few words about this. And since I'm not an active scientist any longer, I will have to do this as a science manager. I think very important in the topic. And when you asked me, I didn't really know what to say, so I sat down yesterday evening and wrote a few things which came to my mind, as you said. And we know that astrobiology can be performed, so to speak, that type of research can be performed in Earth laboratories and on ground in various ways. But space is also important, and for one thing, I think it's easy to understand that when we know that quite a bit of astrobiology is to know and understand how life can exist on other places outside of the Earth, on other planets, be it in the solar system or outside of the solar system. And clearly, if one wants to understand the life conditions on Mars, for instance, one has to go there, dig and analyze, and perhaps results eventually bring matter back, and then we're talking about the space mission. And the same thing is true if you talk about possibilities for life outside of the solar system, on other exoplanets. Then you also need space missions, and I think you saw previously one such mission, which I will come back to. So the space, let's say, connection is very obvious, and I think this became even more obvious, I think, some years ago when NASA decided to go into astrobiology. I mean, the discipline as such is very old, of course. It's not a new invention, but it became a kind of a new invention when NASA put some PR money into the thing, and it became very visible to the rest of the world. And I think there are many who are trying to benefit from that, actually. So my own and the Space Board's involvement in astrobiology started something like 10 years ago. And you will see it more later, René. But it started actually 10 years ago, and it came into being because I was the Minister of Education and Research at that time, actually forced more or less the representatives of the various funding agencies to form a small group, and we should deal with multidisciplinary research and gender issues, both very trendy things, right? And we did this, and we didn't know exactly what to do with it, because, I mean, the task was rather diffuse. So I took the opportunity then to say that one aspect of multidisciplinary research could be astrobiology. And that ended up with, I mean, it was well received by my colleagues, and it ended up to start with a joint workshop in Sigtuna in 1999, where several of you were here. Britt-Marie was there, Göran was there, René was there, and Nils, I guess. Quite a number of people were there, and that was, for me, the first meeting where we tried to see how we could deal with the thing, and I think we had some quite interesting discussions. Some were very skeptical, some were enthusiastic. We had Swedish scientists and invited experts from outside of Sweden. And then I think the thing has grown since then. I'm not saying because of that, but it has still grown by its own strength. And what we've done from the spaceport side is that we've been able to fund special projects, astrobiology-related projects, and we've funded a few PhD students. we have been, I would say, promoting the establishment of the SWAN network, and also put a small amount of money into it, not very much, but still I think it has been a rather important small piece of money. And we've also tried to support various workshops dealing with astrobiology issues. But as I said, I mean, we don't have any special money for astrobiology, so therefore I think it's extremely important that more funding organizations and bodies can contribute to the thing, and therefore it's extremely nice to know and see that this research school has been created at this university. I think it's very, very important. As it is that we have got the Nordita here and having Axel Brandenburg, is that also taking playing a very big and important role in this. I think it is important to have some, let's say, bodies of this kind, because it makes the whole thing much more robust and solid, and it makes it also easier for the funding agencies, I would say, to support smaller special projects, because you know that it has a home site somewhere where it can live and flourish, and where you have the environment that you need to make a small project live in a good place. So I think this is very important indeed. So I think that the Stockholm and perhaps also the Uppsala area will be a kind of astrobiology hub in Sweden, which I think we can benefit a lot from. So that were some side remarks, and then I'm coming to the space missions and space issues more concretely. And first of all, I think, I mean, some of you know this very well, and some of you may not know it, but many of the space missions that are already operational or being planned or soon will be launched are in one way or another useful for astrobiology research. I think of missions like Mars Express and Venus Express, missions that are now, or probes now orbiting these two planets, Mars and Venus. We have Cassini-Huygens, you know, this probe that landed on the surface of Titan, which is certainly of astrobiology interest, and the data are still being discussed, and the Cassini is still, I mean, producing data. We have Rosetta on its way to this comet with a very strange name that I cannot pronounce. It's a very strange name. It will come there in 2014, I guess, yes. And we have Corot. I think I saw that on one of the things we looked at the business meeting. I mean, this Planet Hunter, that is the French ESA mission, which looks at transits of planets around in front of other stars, which is also astrobiology related. We have coming Herschel, the next big sub-millimeter far-infrared telescope, which will be launched next year, which has also a lot of astrobiology aspects of it. And you can name more. So these are then, I mean, this can be used. And if you don't know much about these missions, you can always go to the ESA website, ESA.int. Is it so? Let's say ESA.int, that's it, yes. You will find the description of these missions. And if you want to know more about Corot, for instance, which is a rather new mission, you could always ask our friend Malcolm Friedland, who is a Swede who happens to be the ESA project scientist of that particular mission. So he would be happy to tell you more about it, and perhaps that could also be a way to get into the mission if you contact him. I don't know. You have to ask him and he will tell you. So what about the future, which may be more interesting for you, perhaps at least the younger part of you in this audience and for the school? I mean, what you can look forward to. And first of all, I think it's useful to recall and remember that the theme called life in the solar system and elsewhere in the universe was actually seen as one of the scientifically highly ranked themes of the ESA Future Science program, when there was, let's say, a call for ideas or themes some years ago. So, I mean, this is certainly, I mean, astrobiology of a certain kind at least. And I know that, and I will look at René and others here, I know that many European scientists feel a bit upset now when I say this, because there has been now a first selection round of new ESA science missions. It has just taken place, and the ESA Science Program Committee will discuss it next week. But there, the most, let's say, I mean, the most talked about mission within this theme, that is the Darwin mission, we saw it here. How do you Just wait a little bit. Sorry?
Stryk lite över plattan. Sådär.
Yes.
Yeah, there it is. This is a mission which is called Darwin, which is, as we discussed and studied for a long time, and René Lesson has been one of the very knowledgeable people there. And the purpose of this mission is to detect Earth-like planets around other stars, nearby stars, and also then to observe them, to characterize these planets and try to detect water vapor and ozone, I think, and the carbon dioxide to, let's say, confirm or, let's say, hint at the existence of a biosphere. But this mission was certainly proposed for this new round of new missions, but for its launch slot in 2018. But it was seen as one not mature enough from the technology point of view, so it was not selected for a slot in 2018, but for technology studies. I mean, many people are upset about this, and I will come back to this a little later. I mean, the science committee of ESA will discuss this. I don't think that, I mean, the proposal of the advisory bodies will be changed in this respect, but I still think that we can push for a very aggressive technology program so that this can happen sometimes in the future, because I'm completely convinced that this type of mission will have to come into being one day. It will not be in 2018, but it will be sometime during the decade after that. It's long into the future for many of us, but for some of you, it's still, let's say, within your horizon, so to speak. So let's keep that in mind. So, what about the new projects then that have been discussed? In fact, many of the projects, 50 new projects were proposed to ESA during this last, let's say, announcement of opportunity, and out of 50 proposals came in, and quite a number of these are actually of interest to astrobiology. And how do I proceed with this? Spacebar, yeah. And I've tried simply to list the missions that were selected out of these 50. And I make a distinction between large missions and medium-sized missions. It's a matter of cost. One large mission will be launched in 2018, that's the plan, and one medium-sized mission in 2017. That it's not coming earlier than that is because you need technology work to be done, and you need the money to do it. And that's the reason why I have to wait that long. But if you look at large missions, there are two proposals, Tandem and Laplace, which are directed towards the studies of Saturn or Jupiter and the moons. That is Europe and Titan and these moons. And the plan is that there will be a selection between, first of all, between these two, which should ESA go for, and then there will be a competition between one of these with Zeus, which is an X-ray observatory, not really of interest to astrobiology, and also there's a competition with another mission called LISA, which is gravity wave detector. So, but there is still a chance that one of these missions will be proposed for launch in 2018, and this will certainly be then of interest for many of you, or could be at least. And as I said before, Darwin will be there for technology studies, so that will bring it forward for the next round, hopefully. Then among the medium-sized missions, there are two quite interesting ones. One is Marco Polo, which is actually a mission which will go to a near-Earth object and to make a sample return. That is to visit that body, whatever that body will be, and bring material back to the Earth for further studies in the laboratory. And another one, Plato, is a planet transit and stellar seismology. It's again a mission which will detect Earth-like planets which will pass in front of stars and dim the light, and from there on you can find the light curves and deduce what kind of planet it is. But this will still not be good enough to, let's say, study the planet. It will only detect Earth-like planets around nearby stars. So this is what it looks like in terms of the future regarding ESA. And then, of course, there are also other agencies agencies outside of ESA have their own programs. We're talking about NASA, we can talk about the Japanese JAXA, we have Russians, and we have Chinese and Indians. So there will be certainly a number of space missions which will address issues of astrobiology, let's say, profile. And I think it's a matter of trying to get involved, to try to know about what missions are planned, ongoing, and keep in touch and try to get associated with the scientists involved with this. And I think the way you can do this, of course, is to prepare yourself. I'm talking now to many of the younger here, theoretically, experimentally, or making that you are capable of building certain instruments, or that you can do that you have certain skills that these other people of the projects simply need. And then, staying with ESA, there is also another program which is called Aurora. That is the other missions were within the mandatory science program of ESA. And there is an optional program which countries can subscribe to or not, depending on what they want to have the money for. That program is called Aurora, and that has a very, very specific goal. That is to eventually send humans to Mars. But that will take a very, very long time, and you never know if it will happen at all. So in the meantime, there will be robotic missions to Mars in the first instance, perhaps to the Moon as well, but in the first instance to Mars. And there is already such a mission being developed, and that is called ExoMars, which will be launched in 2013. It's a big mission, and it will have a lander and a rover. And you see the rover, it's an artist's impression of the ExoMars rover. And this mission will, of course, bring a lot of new knowledge to European scientists and also a lot of new questions. It will then, according to the plans and depending on the amount of money that the ministers will decide that the program shall get, to have a Mars sample return mission, which therefore will go to Mars, send down a digging machine, bring matter back, and bring it back to the Earth for further studies. This will happen, hopefully, sometimes at the end of next decade or in the beginning of 2020 plus something. So again, I think that efforts being made today to find the good ways of studying material either in situ, on the planet's surface, or when the material is coming back, are indeed very useful preparatory studies. I mean, useful in their own sense, but also for these studies. And again, I mean, also here, of course, there are a number of other agencies doing this type of work. And the exploration, let's say, again, the concept of exploration in this interpretation, again, comes from NASA, with the Bush, let's say, talking about this exploration and sending people to Mars. We don't know what will happen to the American initiative when there is a new president, but most likely it will continue in some way. And that is at least, I mean, the messages we seem to get. So I think the momentum it has got is such that it will survive. Exactly how it will survive is difficult to say. I mean, the risk is, of course, that the exploration initiative in America will be so much focused on moon and sending man to moon, not for scientific reasons necessarily, but for strategic reasons. But we will see what will happen there. But there are also other agencies doing the similar type of missions. Unfortunately, there is very little Swedish, or I would actually say today, no Swedish participation at all in the ExoMars mission. Some people try to do it. I think Niels was one of those. But I mean, there was a number of proposals coming in, and then it has been de-scoped in the meantime also. So there is no Swedish concrete participation in it, which I think is unfortunate. So I hope that it will be very different when it comes to the Mars sample return mission. And I would still say that if you are eager to do it, there is certainly still room to get involved by approaching the proper scientists. I could also say that the ESA's project manager of this rover is actually a Swede working for ESA. His name is Anders Elving. So I mean, it's always good to have these, let's say, ways to get into the system. So having Swedes in this international organization is quite useful. sometimes. You should deal with it with care, but still try to make use of it. Another possibility which I think should be mentioned also, and which I'm not an expert in myself, but which is more difficult to value, is the possibility of making experiments in microgravity when you are in space, in orbit around the Earth, and that where you can actually, experiments in microgravity and also in the, let's say, interplanetary environment with half radiation and so forth, which may also be of astrobiology interest, but it's difficult to know to what extent you need to go to space to study these things. Clearly, you need to go to space to get rid of the gravity, but how important is that in these respects? I think that is, experiments of this kind are being made, but I think, I don't know whether Brittmeier and others have any comments on this, but it's, microgravity experiments are quite popular in some areas, but to what extent they will become even more important in the future is difficult to say. We will have a European laboratory attached to the space station within a few months, that is a Columbus laboratory, which will of course open the possibilities of proposing more advanced missions, but to what extent it will be important or not for your science, I'm not actually the one to judge. So I will not say much more. I think what I have tried to do to show to you is that, or demonstrate, is that there are indeed quite a number of space opportunities for those of you who are willing to spend the efforts to do it, and also who are prepared to wait for the opportunities to materialize. But in the meantime, I think it is important to be able to wait this long as you may have to do for some of these experiments. I think it is very important that it is possible to mix ground-based and space-based work. That you can do, let's say, laboratory work, modeling work, and theoretical work, and also instrument development. That you can do these things, for their own sake. And it's also important, I would say, that there is collaboration between various bodies. Clearly, many of these missions that I mentioned, these new ESA missions, cannot be conducted without international collaboration simply because of the cost. But there is also other reasons to try to collaborate. First of all, between the disciplines, between funding agencies, between the universities, and also between the Nordic countries. I think it's also very important to have this collaboration, because if one can manage with this collaboration, there is also a chance that what I think now should be called the multidisciplinary science as astrobiology, that can turn into something which is more of an interdisciplinary science, where the things are being more integrated than what they are in a multidisciplinary thing. So I think there is a transition there which I think one has to hunt for, but still be a bit careful so that you don't take the step too quickly, because then you can run into other problems. That is, I think, an experience that exists. And finally, I would say that this is a very small meeting, but still, having meetings of this kind, I think, is very important, especially if you have the Nordic countries involved, because it can certainly help to foster a better Nordic collaboration within this discipline. And I can say that space science used to be quite an important discipline for Nordic collaboration in the past, but I wouldn't say that it is so today. So I think that it may be that astrobiology could be one way in which there could be a positive change, where it could actually promote further collaboration between the Nordic countries. So if that could happen, I think it's something we should really try to promote, as I say, and look forward to. So I think this was all I could bring together, without knowing what I was going to talk about. So I thank you for your attention. If you have any questions, please ask questions, and I will try to answer.
Thank you. Thank you.
You mentioned the sample returns mission to Mars. What are the current plans at NASA for this?
I don't think they have any plan. They probably have plans, but I don't think they have a mission for sample return. What they have is a mission which is called, it's a laboratory, Mars laboratory. I don't remember the name. Does anybody else know the name? It's a laboratory that they're going to send to Mars in 2010. So apart from that, I don't know about any concrete plans for sample return mission. But clearly, I mean, sample return must be the ultimate thing to do to be able to study this material. And that will happen long before a man is putting his or her foot on the soil of Mars. That's clear. So, yeah.
What is actually the state of? Maybe I should really. Is the state of life detection systems? Is Sweden involved in? I mean, if you go to Mars with a robot and you want to detect life, we need machinery small enough, and that needs to be purpose-built, very specialized equipment. Who is doing this? Is Sweden doing anything in that?
Sweden is not doing much necessarily, but I would say that those who are involved in this, I mean, Niels is partly involved in studies of this kind, and also Thomas Hude, who was one of the first astrobiology PhD student, who is now working, as you know, probably in America. And he is having a project together with Lausma and others in Borås, where they're actually trying to, let's say, invent an instrument which should be capable of let's say, studying material in such a way that you can see whether it's just a geometrical structure or biological origin. Mm-hmm. So I think we are, I mean, that's actually, I would say, the area where we are to some extent involved, at least in the preparatory studies. And I think if one can go further in that direction, that it will be a possibility to play a role in these future missions. But as I said, I mean, the timescales are long, so one has to be able to cope with these timescales to survive in the meantime. I think it's. And Nils, do you have any further comment on this? I mean,
the only thing would be that Sandra will talk tomorrow. She's funded by the Spaceport and works with Lausma at the SB.
Yeah, so, exactly.
Yeah.
René?
You know, I'm guessing that a large ESA mission would not be able to afford to fly on the Jupiter mission a lander with a drilling equipment. What happened to the hotly debated Europa mission?
I think that is part of this. Was it Laplace or was it? How do I get back to this one now? Okay, but I mean, there were two big missions, Tandem and Laplace. I don't remember what was
Tandem was the Saturn.
Okay, so Laplace must be the other one then. And in that mission, I'm completely sure that there is a proposal for having a lander for Europa. Yes.
So they are foreseeing collaboration.
Yeah, I mean, in these big missions, I mean, they cannot be conducted without collaboration, because the cost cap of the big missions here is 650 million euro, and for that you cannot make a mission of this kind. And the same is true for Darwin. I mean, and also for this LISA, I mentioned the gravity wave interferometer, and there I know that unofficially the cost estimate by NASA of that mission, which they will take part in it, is It was 3.8 billion US dollars for that mission. If say that is 3 billion euros, then and Europe, ESA can come up to 650. So yes, ESA needs collaboration for all these missions. I mean, it has to be global interaction, I would say. Otherwise, it won't happen.
I mean, you mentioned Darwin, and you said you were going to comment on this. I mean, what I say now, this is going to be subject to technology studies, but that seemed not to be a completely valid argument.
No, but the thing is that, as far as we know, the message to the, let's say, the lower level advisory bodies dealing with these missions was that the technology was not mature enough for Darwin to propose it for a launch in 2018, whereas a mission like Zeus was, but a mission like Zeus was judged to be such.
Zeus was, yes.
And I mean, I have seen no, let's say, written documentation supporting this statement. So this is one thing I will ask for when I come to the Science Committee meeting next week, because that is an obvious question. And I can also say...
an honest statement here, that since the message has to be spread around, it is a fact, a matter of fact, that Zeus needs an absolute higher accuracy of free flying than Darwin, because Darwin has delay lines for compensating the optical pathways, which you cannot do at X-rays. This is a fact, okay? So to claim that this mission is more mature, it's a sheer lie.
I totally understand that you're upset, and I think many others are as well. And we will see what the answers will be. And the interesting thing is that when I read now the official document for the meeting coming from the upper level executive, what is being said is that none of the large missions now being proposed for a launch in 2018 are compatible with such a launch date, considering the technology as it is today. So I mean, we will see. I mean, it's so what I can say for sure is that all of these missions are not only costly, but they're also very challenging from the technology point of view, which also has also is a reason for the high cost, of course. So we'll see. I mean, what will happen, but. As I said, I'm convinced that the Darwin, let's say, scientific goal will have to be included sometime, but it will take some time, I think that's clear. So the question is, I mean, I will still be trying to give an optimistic view for those who are young enough to be able to plan for this.
Renee has another.
Just to clarify this, my interpretation of what you are saying is that the spaceport likely would look positively at continued both scientific and technology work which is aiming towards Darwin. Is that correct?
Yeah, I mean, it's in a very general sense, I could say yes. I'm not saying that that means that I'm saying anything about any applications right now, and I have the chairman of the science committee sitting there. but I think this is the only mission where both the Astronomy Working Group of ESA and the Solar System Working Group of ESA and the Space Science Advisory Group of ESA, Committee of ESA, all three are very, very specific in saying that this is an important mission where one should do technology work for. So I mean, it's
yes,
also,
but that's on the ESA side. I was thinking on the Swedish side.
Yeah, but I think it's what we will do. I think we will have to, let's say, take the perspective of what's going on in Europe as a whole, because with this type of missions, I mean, if this would not be promoted at all within ESA, I mean, why should we try to do it?
Exactly.
So I mean, something has to happen there, and then we'll see how we deal with it here. I mean, it has to be, it must be meaningful to support it at home. I mean, and that can only be meaningful if it is also supported elsewhere in one way or another.
Sure.
I don't know whether, Mats, if you have any further comment on it.
But is there going to be a decision as we see next week?
No. Actually, this proposal to come up with these missions is a pure executive proposal. The Science Committee at this point in time is not asked to approve anything or confirm anything. We're just asked to note and comment. That is the ESA vocabulary. And that means that we are, of course, prepared to ask or invited to ask questions and to even criticize the thing, but we are not there to approve it. So that will not happen until 2011, I think, if I'm right. Then we will come to a point where SPC, as let's say the delegate body, will have to say yes or no to the proposals. But I mean, that's according to the convention of ESA, how these things are being developed. So the advisory bodies are the advisory bodies of the executive. But from a scientific point of view, I would say that they try to make them biased and try having the expertise that is needed. But I mean, that can be also debated whether that is so or not. I mean, we shouldn't have that discussion now. But I think it's more delicate when there is a saying that this technology is not mature enough, because then you're actually listening to internal views of the ESA executive and not of any independent experts. And that's, I think, what upsets people. I mean, that you have the feeling that, I mean, every person is an individual with his or her own bias. And I mean, yeah, we will see what happens.
Okay, great. Thanks very much indeed. And now we come to Samuel Angel. So he will be talking about the protoplanetary disk modeling that he is doing in Uppsala, and in particular he will focus on the vertical disk structure.
All right. Hello, and thanks for inviting me to talk. I'm doing my PhD in Uppsala, and I'm going to, since it's a rather diverse audience, I'm going to give a little summary on why planetary formation is of interest, also in the astrobiological sense. First of all, to understand disk formation, planetary formation, you need to have a grasp of stellar formation. A star is formed out of a molecular cloud of gas and dust by gravitational collapse. Collapses onto itself, getting hotter and hotter and more dense until fusion starts, and you have a star forming. Now this is not shown on these images, just focus on me for a moment. As the star has been born, the gas around it is not just disappearing; it's still continuing to fall in towards the star, and it rotates by the physics of this situation. And as that happens, it slowly moves and falls down into a disk. Now, what we are seeing here, the thing is that, of course, that a star is not born in isolation. It's born surrounding a cluster of stars. And what we see in these images here is actually a nebula, where you have a lot of hot stars, which are born and can grow much faster than other stars. They are up on this edge. And you have these gassy clumps, which you should see here. See, it's lit on one side from the stars on the left, with still a lot of gas. This is a big construct. I mean, this is much bigger than the solar system is today. And still with a lot of gas around it, and this is an infrared, but you get this little dot in there, which is the newborn star forming inside. Eventually you have this gas cocoon being blown off, and what it remains is, as I said, is this gas structure, which is a sort of a disk structure, which continues to fall in towards the star gradually. And as it does, it becomes compact down into a thinner and thinner plane, a disk plane. Now the star does not stop evolve because it has started fusion. It continues to. It's still not quite a star. It's a very young object looking very different from the sun, for example, we see today. As we see this matter collapsing into this, see if I have the. Yes. You have the matter being packed closer and closer and closer, and the gas and dust particles being packed together more and more. And what happens is that we start seeing things getting so close to each other they start to connect. And you build up smaller structures, which like the stuff you get when you erase something with rubber. These build up bigger structures, and a theory which is most prominent these days is that these continue to build, moving around in this rotating protoplanetary disk, which is called, and eventually they will grow big enough to form planets. Now, there are several problems with this. First of all, there's a time issue, because the star is evolving, and eventually, within a very short time frame in astronomical terms, tens of millions of years, it will simply become so bright that it evaporates the disk away. And when that happens, there's no more material left around to continue to grow these planets. Secondly, you have the issue of the actual growth of material. This is something which is very interesting for us astronomers to collaborate with solid physicists, with geologists, and so on, in order to understand exactly how this process works, and how also what kind of optical properties and so on. How can it actually grow throughout from just something which is as thick as cigarette smoke to a planet? Eventually, anyway, you will end up with clumpy stuff and eventually planets. Now, the theory goes that if you're very fast to grow this big planet thing, and there's still a lot of gas around, it will vacuum up a lot of stuff around it, and you will have a giant planet, Jupiter, Saturn, and so on. If it's too slow to grow, so it's still not just some unshapely thing when the sun or the star goes off the disk, it only remains some unshapely thing, and we have asteroids, Keplerian objects, whatever. Finally, depending on where it's formed, you can end up with something in the middle, which is a terrestrial planet, roughly. Now, as I said, there are many problems with this, which I will not delve into it, but point what I'm trying to make here is that the disk and the structure of the disk in which this happens is of great importance for what kind of planets come out, and well, if you understand how this process happens, you might say something about how common planets are in the universe, for example, and what kind of behavior they would be expected to have, the habitability, and so on. Because the thing is that when we found planets outside our solar system, around other stars, we found that they didn't look at all what we expected them to look like. We had only one point to look at before, right? We have our solar system, nicely behaving circular orbits and the whole thing, with terrestrial planets inside, and we have giant planets outside. But suddenly we found, around other stars, we found that we have giant planets moving closer to their stars than Mercury is around our Sun. We have planets moving in eccentric orbits. We have essentially a whole range of, probably almost an infinite range of different combinations, which is still being explored, and I think it's around 250 planets now, I think, which is found outside our solar system. It increases weekly. Well, if you want to study the disk, and this is what I'm doing, the protoplanetary disk. This is a schematic of the structure. You have the star over here, and we're seeing it from the side. Okay, so the disk is stretching up in this direction. So essentially, the matter is falling into like this while rotating. I'm studying the disk at a stage when there's becoming thinner. The disk is getting thinner, so it's not a huge amount of matter going on. And the main point here is that the friction of matter in the disk is not the main heating source, but the actual radiation from the star is what's heating the disk mainly. As you see, it's a flared structure, which affects, and you have what the effects of energy in the structure is the light from the star coming in. Of course, if you think about what I said in the beginning, when you have stars not forming in isolation, when it's huge clusters of stars, you would have nearby stars actually radiating with cosmic rays and X-ray and UV radiation. But this is the basics of this thing. Now in Uppsala, I'll skip this bit. We are treating this from two approaches. This is something Axel recognizes. Vladimir Lira is treating the disk in a 3D hydrodynamic model, where he puts a planet in and runs it through time. This is the details of this model. Something actually could probably explain much better than I could. But it has many powerful features in it, like the effects of turbulence, and also a gray radiative transfer treatment in it. The problem with a three-dimensional code currently is that there is a limitation on computational power. I mean, what you can actually treat with this thing. If you want to have both a high resolved 3D structure with hydrodynamics and so on, it's getting difficult to also have a high frequency resolved radiative transfer going on in this thing. So what I'm doing is taking on the one-dimensional case. So I'm treating the vertical structure of the disk. Actually, I'm treating a 1D kind of code, because I'm actually solving the radiative transfer from the star as well. But I'm only doing it sort of in a radial direction, and then I calculate the effect of the re-radiated light, because you have light from the star hitting the disk, heats stuff in the disk, and then the disk re-radiates as infrared light. This is what we see. This is what the image that you saw in the beginning. This is huge structure, which you can actually observe directly. You can't see the planets themselves yet, but you can see the disks. That is why we know this is a good thing. So I treat this in a one-dimensional way, and I combine this with Vladimir's three-dimensional models, taking sort of pinpointed positions in this disk to solve the full radiative transfer in those positions, using sort of his model as a restraint in a way. And what you get is a full vertical structure with a consistently solved temperature and density and so on. What you can do with this is that you can do it similar way to a stellar atmosphere. You can solve for spectral analysis. You get spectral synthesis out of it. And when you have a spectral synthesis out of it, you can compare it to observations. Now a disk structure this is an example where you have so this is actually tilted on the side. So this is the midplane of the disk, and this is the surface of the disk. And you have the temperature here, so it's actually hotter, of course, on the surface, because that's where this is at 1 AU, and this has an Earth distance from the protosun. So it's actually hotter on the surface and colder in the center. And of course, when you have these things, then these things starting to get interesting. Well, this is a solution of. First, this is also as an example. You see the disk actually being formed out to 100 AU in this case, and you have a spread of temperatures going from the closest part of the star, which is of course very hot, going out towards 100 AU, dropping gradually outwards. What happens chemically in here is how will this behave? How will the structure of formation of the planet be affected in various situations here? This is something which will be treated, which is currently not doing, but this is the next step which will be done. For example, putting in a planet in the disk, and it will move around, and when it does, it will form waves. Density waves, and it will form gaps eventually, opening up, simply vacuum out parts of the disk, sucking it to itself. How will that affect what you see? Can you see that effect clearly in observations and so on? This is the kind of results we will get out of this. The code is currently in testing, and we're taking observations with APEX Laboca instrument in Chile, which is, for those those interested, it was the first time this interest in this new instrument is tested, and it's actually this is the first telescope in what will be the ALMA array eventually. Now, stepping away a little bit from the disk structure itself, you have a parallel project related, perhaps more related to astrobiology directly, because of course understanding the disk structure and how it relates to planetary formation in the long run is astrobiology. I mean, without planets, as far as we know, that's having a planet is a good start for life, as far as we know. But we have also the issue of water on Earth, and this is a hotly debated field. Could it be that because you have Earth forming here, right? And the two main suggestions how water came. Either it was a part of the material of which Earth formed, simply water-rich chondrites, for example, and simply. Problem with that is that if you study these models, you will find that the temperature is pretty high in these regions, probably making it very difficult to have water condensate at the place where Earth formed. And also you find little water in anhydrous chondrites that have absorption of water. Other alternative is that you have Earth forming peacefully here, and suddenly it's bombarded with water from the outside at an early or late stage. This is also didn't happen later in the development or before. Problem with this is, where would that water come from? The classic idea is that it came from comets, but there is the amount of water and also some isotope ratio erasiatic problems with this scenario, which doesn't really match from the comets we have visited and seen. And those in the know modeling this directly says it's simply not enough water. What we have seen is that there is actually a lot of water in the outer asteroid belt today. We see that there's a lot of water-rich signatures out there. So what we are doing is sort of testing out the idea that, because what we should remember is that in a disk, in a protoplanetary disk, it's a complex place, and we know for sure that planets move around as they form. They don't just sit in one place and form, but they actually move around, disturb each other, called migration. Quite possible that the Earth was not actually formed directly where it is today. It could have moved, came into its current position from further out, in fact. Quite likely. So one thought is that we see that there's a lot of water out there in our asteroid belt. Maybe that was sort of a passing reservoir for the Earth water. Who knows? So the current work I'm doing is emulating to see if Jupiter, out in its orbit, could actually have thrown in water-rich material from outside the ice line. I didn't mention the ice line. The ice line being, of course, the point where water can freeze. And it's well known that icy stuff is more sticky. It sticks together much better than dry things. So that's an important factor when forming big planets, big things. And that makes a big difference in models where the ice line actually is located. It is also not very clear, because this has to do with how hot the sun actually was and how it evolved, and local behavior in the disk and so on. Anyway, this is something also being worked in progress. I can't give you any actual results on this, but nevertheless, so this is just more of a mood image. It doesn't really show anything that's round. These red dots. Nevertheless, this work which is being done which is related to astrobiology in the sense of water also. And I think that's what I was going to say.
Mm-hmm. Thank you. Thanks, Samuel. Any questions, please? Yes.
When you say that the disk plane is cold, what is the assumption on the disk model?
Assumption of the
assumptions of your disk model. If you have enough mass accretion rate, then you will have enough disk.
yes.
Your statement is not.
This is in Meredith's model. You assume a later stage of the development. That is the point where you probably already have planets, a few protoplanets in place, and at this point, the assumption is at least that you can ignore the viscous heating and have an irradiation-dominated disk. So the main energy, of course, there is still accretion onto the star and heating from that, but it's dominated by this stellar radiation.
So your temperature gradient is negative, so you would expect an emission out of that. Have you any predictions what you will see with Herschel?
Yeah, sure. You have, yes, sure. I mean, you see, if you observe a protostar or a young stellar object, you will see an infrared excess in the spectral energy distribution towards longer wavelengths infrared.
So, thinking about the gas.
Pardon?
Gas emission.
Yes.
Not the dust emission.
No. What you see no, actually, what you see is the dust. Yes. So exactly how much that gas you have in there is observationally tricky today. Actually, no. This is a pretty hot debate.
So you don't have any gas in the disk?
Oh yes, there is, but exactly how much that's another matter.
You need enough in order to pump it up.
Yeah, sure.
Otherwise it will collapse.
Yes, sure.
Oh, I think that's too close.
But have
No,
you been
that's
under
true,
the
but-
impression so far that the disk should actually be hotter than the rim of the disk? That the gradient should be negative, that the temperature should fall off its height? Is that what you have been thinking, yeah? I mean, it is a standard belief is, of course, that the disk is mainly heated still by viscosity. And this is probably still true at early times.
At early time is definitely.
So at what time approximately, at what age of the disk does the vertical temperature gradient change its sign?
But it changes around, well, exactly, it depends of course on what kind of disk you're having, but generally at the point where you have starting to form bigger clumps of planets, essentially. So you're already talking about kilometer and bigger sizes of planets, let's say. Probably even smaller Earth-sized planets at this point.
And by that time, the disk is probably still very opaque, so the planet itself, which is in the middle of the disk, won't get much sunlight at all, of course.
No, this is of course an interesting point in itself, because once you get up beyond a certain point in the disk, the dust itself sinks it's close to the midplane, right? So that's cold material, which is and beyond Iceland that is icy material, likely, which is good at sticking together and forming things. Whereas you have a warm and a hot layer, it's sort of an inverse stellar atmosphere at this point, essentially. You have heating from the surface rather than from the top and from the bottom. So, but you definitely have two constituents. So it's the two parts of the opacity of the disk. One from the dust and one from the gas.
Alexis?
That was actually my question. Are you able to study that settlement in your model?
No, currently not.
For the first time?
Yes. That's very important. It's very important. And it needs to be implementing a full chemical, a full dust formation structure, and eventually opacity evolution. The whole thing.
You have been mentioning some interest in collaborating with geophysicists. Do you have actually some ideas or possible approaches to calculating the evolution of the planet's surface temperature during the course of time as a result of even things like bombardments?
Well, it's not...
And age, of course,
well,
cooling.
Models like this, of course, can give boundaries to such a modeling. I mean, you have, sort of the outer... and this is of course of great interest to the planetary formation scenario. Of course, it says very little about the actual life conditions and so on. We know for sure the planets today don't have retained their primordial atmospheres. It's very interesting for the formation modeling itself.
Okay, any other questions? Oh, yes.
Yeah, well, I have two questions, just because as a biologist I don't know very much about the basic things here. One is what initiates the whole formation? How do you get started?
You mean already from the stellar stage?
Yeah, you say you have a cloud and you end up with a planetary system.
Yeah, in the galaxy you have huge gas and molecular structures moving around, and these are on very large scales. We're talking tens of we're talking parsec scales at least, and these clouds move and interact with each other. So you have a part of this gas cloud or molecular cloud reaching certain, getting disturbed by something, a collision with another cloud, passing of gravitationally disturbed, and some part of the cloud simply becomes a little bit denser than the rest, beyond a certain point, so it starts collapsing, and that's sort of how it happens. And eventually, as stars start to form, the remaining gas gets sort of spread out and can be part of the new moving around material that will eventually start new processes. So it's not always clear to say what started the stellar formation always, but for example, galaxy researchers, for them they can pretty clear if you observe extra galactic galaxies, other galaxies. For example, you have galaxy mergers and things which actually very clearly start formation by purely simply colliding huge masses of gas and thus starting a slow process.
So you can actually observe these kind of things. It's not just
outside, around in other galaxies. Yeah. But today, also in our galaxy, of course, we see large star-forming regions. So this happens all the time. So these images I showed you, that's ongoing things.
So even on a much larger scale than this, it's just the
this is just
the whole thing is part of a much bigger picture of everything being turbulent. And just where the turbulence has enough compression, self-gravity can eventually take over.
Yeah, so this is just a small piece of this, and this is just a small piece of the nebula or the sort of cloud which contains many stars being formed.
And another question: how comes that our system is so nicely sorted that you have these? You know?
Yeah, well,
9 planets or 8.
It would be nice if I did know. I mean, it's sort of a chicken or egg situation. Is the solar system so nice because we can see that because we are here, or it would just simply have to be? I mean, thing is that probably the very physics of the protoplanetary disk is so complex that just a small change in the initial conditions will completely change the outcome. Actually, there's so many factors that come in. So personally, I'm a bit skeptical as to where you would have a nice, neat classification of these things, or being able to predict exactly how a planet system would come out, start seeing how they come from beginning to end, so to speak. Statistically, you could do it, maybe, but that's something which we're still finding data on new planets constantly. So, and there are planetary systems which are kind of nice too. with very different sort of distributions of things compared to others. So there's no solar system replica yet. But of course, you can certainly discuss if the our Earth is located very conveniently at a distance where the water can be liquid, and we have a magnetic field around us to shield us from the effects of the sun. If you look, probably Venus is probably a more classical planet, terrestrial planet than Earth is. Look, Venus is a very nice planet in modeling sense, but it's completely uninhabitable as far as we know. There's not a big change in position. It's just slightly closer to the star, and has no plate tectonics going on. Going the other way, you have Mars, also in the habitable zone, but slightly smaller. So the differences are not big, but they're very different worlds compared to that. What this actually say is hard to tell. I mean, it is very difficult to know.
They probably lost their plate tectonics, right? They probably had it.
Yeah, they had it, but lost it probably. And so there's also another thing. I mean, you have plate tectonics, which is probably helped by having liquid water, and that liquid water, in this case, in turn, it's sort of a bad spiral. How the stability of life is difficult to establish, I think.
Okay.
Yeah.
Thanks very much. Now we have Kai, who needs to have a computer now. Maybe you can either borrow yours or or otherwise the Macintosh, and Anthony will help him.
Which?
I can't stop myself. I have to be honest with our fellow scientists. The birth of a star has not been observed. This is a challenge. We believe we know exactly what happened, but we have not seen it yet.
Exact
We should not give the impression that we have everything on our 10 fingers. We don't.
We have seen like every stage before or after, essentially.
Yes. You have seen the big belly, you have seen the kid growing up, but when it comes out of the womb, you haven't.
Okay.
Why not? Is it taking place in such a short time? Or what is the
Shielded in the
Deeply
south.
Oh, it's not like, sorry, I didn't know. From you. Yeah. And at the point, it was very faint.
I think it is contamination. You have to get rid of the background because of the outflow. The only way of observing the thing we know of by looking at the variation.
So we now have Kai Finster from the University of Aarhus, and he will be talking about Mars simulation experiments.
Yeah, thank you very much. I have attended several of the Nordita meetings, and I found them always very inspiring. So this time Nordita was in Copenhagen, so I'm happy to attend another Nordita meeting, and I hope that I can come with some new inspiration, go back to Aarhus. And I would very much like to discuss with you the value of biological mass simulations. And this was the original title. It's the effect of a long-term mass simulation on microbial permafrost community. That is an experiment that we were doing in Aarhus. We actually built an instrument which is a proxy mass simulation instrument. I will show you a picture of it. I will just, before that, I will just introduce a bit to this topic. I don't know how many biologists there are in the audience. So this is going to be a more biological talk rather than a planetary or astronomers talk. So I talk just a bit about mass simulation experiments that have been around for quite some time, and I have compiled a bit of it, an introduction. I will demonstrate our facility, the outcome of the experiments that we did, and more interesting at the end, discussion of the value of these kinds of experiments. So this was just a graph showing number of experiments, and this is the time scale. You can see that there have been done different kinds of mass simulation experiments. In most cases, prokaryotes, let's say bacteria, have been used for these kinds of investigations. Mainly pure cultures, here starting in the 50s and then in the 70s. This is the just before Viking. This is the Viking crisis, when people hoped for detecting life on Mars and failed. Well, it's still discussed. It's not sure. Some experiments said no, some maybe. And well, it's probably a question of strong belief at the moment. What came out of it? This is the Allen Hill area, where the Allen Hill meteorite was examined, and there was a big show by NASA done on this meteorite and a lot of the experiments that came after it. And it was also the start of actually the astrobiological era. Astrobiology has been around for many years, but at that time it was really boosted. NASA convinced Congress to invest a lot of money in astrobiology. A lot of my colleagues profited a lot from this money that was given. It never really came to Europe. Well, interest was there, but it never really became a funding area. So as astrobiologists or people doing astrobiology research, we always had to compete with other types of research. And I think that's a good idea. It's fair enough. I think it's just going in the wrong direction, having all these small boxes, which are very popular nowadays, money that is already dedicated in the first place to sponsor some kind of research out of competition by other research. So I think it's not a good idea having an astrobiology, let's say, bank account. I think we should convince our fellow scientists that astrobiology is actually an interesting and worthwhile subject to investigate. So, but you can see here, now we are up to here, and a lot of experiments have been done. Most of the experiments actually using prokaryotic pure cultures, single cultures of bacteria. Very few investigating organic material, in general, mainly amino acids, how would they behave to simulated space conditions, Mars conditions, and very few experiments where you actually investigated complex microbial communities. I also had a look on the facilities that are around. I don't know if you can read it. It's just a table with different facilities that have been built around, and these are only the facilities which show up which have some kind of description in a peer-reviewed journal. There are more facilities, and you can find it on homepages of different institutions. So but I just said, okay, I take the ones that people made an effort describing in a way so that other people could validate this is a good approach or not. You never know. We know the review process, so at least some people had an opinion about if these are facilities that should be show off in a research journal. And here are a number of different. Here are just the names, and people also try to explain which kind of experiments can be carried out in these facilities. Most of them actually are dealing with Martian conditions. This is the pet planet for astrobiology. It is close enough, and we can all dream of that real experiments will be carried out on Mars sometime. It's not somewhere far out in the universe, which only can be observed by telescopes. So here is actually a place where we can go to, maybe not in our lifetime, but well, we hope that mankind will exist a little longer and is wise enough to at least protect this planet, and then maybe from this planet is able to explore other planets, but we never know. So here people can't wait, so they bring the planets into their laboratory, and then they try to investigate terrestrial organisms and see how they can withstand and cope with these kinds of experiments. And we in Aarhus, we have been doing this kind of thing. We have been developing our own Mars simulation. Mars simulator, and you see it looks a bit like R2-D2. This is the container here. This is just a schematic drawing. Shows you the different connections and devices that are connected with the container. In principle, it's just a chamber which can be controlled in terms of atmosphere and pressure and temperature. And then we can light on our samples, so we can use all kinds of light sources. We've been mainly using a UV lamp, a mercury sealer lamp, producing a radiation type which is close to what microbes would expect to see on Mars. You can just here have a look inside. This was when the radiation went on. It's quite bright. A window here on the side to see if everything goes well inside the chamber. And the whole thing is rotating, so we can expose different kinds of samples for a decided number of hours, days, and so on, depending on how much time, patience, and money we have for our experiments. And the system is then controlled by computer, so we can make sure that the temperature in the chamber is the same. We can control the gas composition, the humidity, and so on. So we have a very good description of the experimental system that we are producing here. This is part of the Aarhus Mars Laboratory. We actually have a Mars Laboratory at the University of Aarhus, and I invite you to visit our website, which is quite easy. It's just MarsLabDK, www.marslabdk, and then you can read about the facilities that we have. And my colleagues from geology and physics, they are very much involved in ESA projects. So they are currently having an instrument flying with the Phoenix mission to Mars, landing there next May, and they are involved in dust transport investigations. So they measure wind speed and stuff like that. So if you're interested, just visit the website, contact the people. A lot of things are going on there. It's a small group, it's not big, but a very active group of people. And they're always interested in collaboration with others, Nordic people, but also people from the rest of the world. So just a small advertisement for our mass lab. So yeah, we build it in this way to make sure that we have sample enough to study. And these are the conditions that we were able to produce during our first experiment. You can see this is the present mass. One of the things that we cannot produce is the gravity of Mars. We don't know how much gravity actually influences the survival and activity of microorganisms. But we can deal with the temperature, which is within the range, a little bit high at the surface of the samples. This was mainly due to the type of lamp that we were using. It has generated a lot of heat. In terms of pressure, we do quite well. Radiation, we cover most of the spectrum which you would expect on Mars. At least we are in all the radiation, UV radiation, which is interesting for biological systems, is quite well reproduced. The intensity is much higher. It's about 35 times higher than the intensity. It depends on where you are on Mars, but at a particular area on Mars, 35 times higher. And this, of course, has some implications for the biological material that we were investigating. But in the first experiments, we said, okay, we have to put in a little bit more of energy just to make sure that something happens. So this was also a student's project, with master student and PhD student, and they of course it was also necessary that there was something to investigate after the experiment. And now, after having seen the results, we can go in and fine-tune all the different parameters. In terms of gas compositions, we are a little bit high in oxygen and water, and also CO, which are maybe reactive gases themselves, but at least the sources of producing some reactive gases, which then may have an effect on the biological material in our samples. This was just a system that we modeled, that one of my colleagues from physics developed to show you the temperature in the sample. You can see that there's a relatively steep temperature gradient. And it also tells you, well, the samples, they were rotating, they were inside the light beam for about 3 hours and outside the light beam for about 27 hours. It was just
the rotation cycle that we decided. We could have rotated it faster or slower. And you can see that it takes approximately 3 hours before you have stability and temperature at the, well, here it's 2,000 seconds. Just about more than an hour in the top part, and longer in the deeper part at 15 millimeter. You know, it was not completely at equilibrium at after 3 hours, the time when we rotated it out of the light beam. So there is a relatively steep temperature gradient inside of our sample, and this may have implications for the time the biological material can survive under these conditions. When we finished the experiment, we took out the samples, and you can see what we investigated was a microbial community in a permafrost soil sample, and we decided on permafrost because here we have a biological material which is adapted to quite harsh conditions, to low temperature, and also to limited water availability in the permafrost. And well, there's always a problem when you decide on which type of material you want to use. You try to somehow get close to Martian material. Well, to material which has been exposed to conditions similar to Mars, well knowing that it will never be like Mars. So there's always terrestrial material which has some, which has its terrestrial history. But what we did, we used the permafrost material, freeze-dried it, homogenized it, so we were sure that the material in our column here was all the same in the top, in the deeper parts. And after the incubation, we sliced it to different horizons. We sliced it in 1.5 millimeter in the top and 6 millimeter in the bottom, and then we put it together to have enough material for all the different kinds of investigations that we wanted to carry out. And this is just an overview of the different approaches that we used to treat our sample. This is the sample. We had an approach where we investigated the bacteria. We are microbiologists, so we're interested in the living material of in these samples. We just tried to culture organisms from different horizons and see how many bacteria were able to survive the treatment. This would then be used to investigate the survivors, see why are they in particular survivors. Is this just chance? Or do they have inherent capacities that allows them to survive the treatment? We can do some physiological studies, and we could also do some phylogeny, saying which kinds of organisms are we dealing with. We made activity measurements. We just took the samples, diluted, this was after the experiments, diluted it in water, added some chemical compound, in this case it was glucose, radiolabeled glucose, and just see if the bacteria in this environment were still physiologically active. We did some culture-independent approaches where we just looked into the microbial community. Did it change as a consequence of the treatment? And we also counted the number of bacteria, see if the number of bacteria decreased in the sample, and we also did some investigations on the number of bacteria that were dead and alive. There's some specific staining techniques which allow you to distinguish between living and dead bacteria. We were interested in to see whether the treatments changed the proportion of the living and dead organisms as a function of depth. So, and I'll come up with a couple of tables. These are our horizons. You can see we sliced them in 1.5 millimeter depth in the upper part, and then we get more coarse down towards the bottom. And we also have a control sample. The control sample was freeze-dried permafrost material, which was just kept in the freezer instead of being put into our simulation device. So it was treated in completely the same way. It was part of the homogenized material. It was just kept outside the sample. So what we could see here is that we actually could see an effect on the amino acids, which is totally characterizable amino acids. It means amino acids which are part of proteins. And we could see that this is the total number of the micromole per gram dry weight. We see that we in the upper part have 25.3 micromole per gram dry weight of soil, and in the next horizon, which is 1.5 millimeter below, we have 37.8, and this is about the quantity that we found in the rest of the soil. And we saw when we tested it that this was a significant change, and the same happened to amino acids, which are part of the
peptidoglycan of bacteria. Also here we saw a reduction in the concentration only in the upper part. In all the other compounds that we investigated, total organic carbon, total organic nitrogen, and ammonium, so we didn't see any change as a function of depth, and also not compared to the control that we used as our reference. And here you can just see for some specific amino acids, you can see that all the amino acids, just have a look that you have the top point here, which is lower than the next point. For all the amino acids, with the only exception of tyrosine. This was the only amino acids of which the concentration was not reduced as a function of depth in the upper part of our incubation. So it seems that the treatment had an effect, somehow degraded biological material in the soil sample. The next thing we did was just extracting DNA and measuring the amount of DNA as a function of depth. And also here you can see that the DNA this is our control, and these are the deeper parts, and this is the upper part. And again you see that there is less DNA in the upper part than in the lower parts, and also compared to the control. So also DNA was somehow degraded, and this was a pico-green stain. So it was not just that the DNA was fragmented, it simply disappeared somehow, so that it was no longer stable with pico-green. The next thing that we looked at was the number of bacteria that we could culture, and also here you see a significant effect. Somehow this control is a little bit off, but when you compare it, this is within the core. This is homogenized material, so you see clearly that we could not culture any bacterium in the upper part of the soil, only if we used rather large amounts of organic of soil sample that we then could suspend and grow. There was still some bacteria left, but when we used the same dilution, you can see a clear impact on the material down to about 9 millimeter. So there is a difference if we look into the proteins, the DNA, and the number of culturable bacteria. When we looked into anaerobic bacteria, which were cultured in the absence of oxygen, we didn't see a significant effect. We have by now no explanation why the aerobic cultured organisms were in particularly affected by the treatment. This is more for the biologists. I'll go to the next one here. Another interesting observation was that when we just counted the bacteria by staining them with a stain that's called cyber gold, which stains the DNA inside an organism, and then you look at it under a microscope, and you see the bacteria as shining dots in the microscope. You also here see a clear reduction in the upper parts, and this is almost down to about 50 millimeter, a reduction in number compared to what we have below and also in the control. And this experiment here summarizes the results of the live dead stain of the bacteria. So here the darker gray ones is the viable or living fraction of the bacteria, and the gray is the just number of dead cells. Cells which still have DNA, but the membrane of the cells is so permanent that a relatively large molecule can penetrate into the cell. So these cells are then defined as being dead cells. And well, you don't only have to look into the big numbers on this cell from the experiments. What we could do then is we could calculate half-lives for all these different compounds and cells and so on. And you can see that the mass half-life in days, mass in this case is our mass simulation experiment. You can see that there are half-lives in the range of, well, this is our experiments, 25 to about 183 days within the period of time. These different compounds were degraded to half of the quantity that were present in the beginning of the experiments. And here in the lower parts, we just have added some of the information that was available on these specific compounds from other simulation experiments. They were done in a different way, in a different simulator, with a different light source, different intensities, and also different pressures and temperatures. But in generally what you can see here, this is material which was not protected by a soil matrix. And this was material which was directly exposed to the Martian radiation. And you can see here, an important thing is that when you look into the intensity, there is about 300 times different intensity. And so in our experiment generally the intensity was much higher. Still, the survival of the different compounds in the bacteria was much longer, and this was probably mainly due to the fact that the material was protected by a soil matrix. If you expose it directly to the UV radiation, the lifetime is very short, but as soon as you cover it or embed it in some kind of matrix, the survival of the organic material expressed as DNA or proteins or also even cells is much larger. But still the lifetime is not very long. If you compare it to 4 billion years on Mars or so on, but there's very little left after this amount of time. Not surprising that it's so difficult to find anything. So the conclusion, and this is something which I would like to discuss with you, is that we have to, of course, speculate about the different effectors, which could be the reason, what could be the reason for what we observe. And of course, one of the reasons is the UV radiation, which can destroy organic material and kill bacterial cells. That's known. UV radiation is used to sterilize surfaces and so on. So that's not a surprise. UV radiation is also very quickly absorbed, so we don't expect the UV radiation to penetrate deep into the soil. There shouldn't be any much left below 1 millimeter or so. So it's only effective in the upper part, and if you could slice our material finer, we would probably see that there is an effect within this upper 1.5 millimeter of the soil that we were observing. Then one of our speculations is that due to the fact that we have oxygen and water in the atmosphere, there is a potential formation of reactive gases, which could be ozone or other oxygen radicals. And they can probably penetrate deeper into the soil. And this soil is a permafrost soil, which is full of humic substances, and these humic substances may even catalyze the formation of these reactive gases. We have not been measuring this, and this is of course something that we have to do in the future, just to better describe the type of reactions that of which we observe the consequence in our system. And then another thing that we observe is the freeze-thaw cycles, which in this case could have taken place in the upper 5 horizons, where the temperature was above 0 degrees, and freeze-thaw cycles are actually used, for example, to lyse cells. So they would be very efficient in destroying not organic material, but at least cells, and this would explain why we see a change in cell number and surviving cells also in the deeper strata of the soil that we've been using. So but one of the questions is, or the open questions are, what happens to the organic compounds? So we see that the amino acids are disappearing, the DNA is disappearing, but they don't show up as organic matter. We don't see that in general the organic matter is disappearing. And the next question is, what happens to the cells? There were cells when we started, and they have disappeared. They have totally disintegrated. The DNA has somehow disappeared from the cells, so they were no longer stable. And then, of course, the most important question is this a useful approach? Or does it make sense to investigate terrestrial material when you address questions about life somewhere else? I know that most of the astrobiological community is actually working on terrestrial sources, and when you ask the question whether this is astrobiological purpose or whether this has some implications for astrobiology, they always say yes. And when you have a look into NASA's roadmap, it's mainly written by people that work in extreme environments, and for them it was also a way to finance their interest in extreme environments. So, and the argument is usually, well, if we find organisms in extreme environments on Earth, then well, why not outside Earth?
So this is something that I would like to discuss here. Is it a useful approach? What do you think? And concerning our system, what should we improve? Do you think that it's anyway valuable to do these kinds of experiments? And the next thing, if you think so, and you have students that are interested, or yourself, you're interested in doing experiments in Aarhus and using our facility, I would like to invite you. Come there anytime and use it. We build it, and well, now it's there. And there, instead of building your own facility, then you could come there and spend some time in our lab. So, thank you.
Thank you. Hi. Questions? Let's start with Samuel.
You said that you saw some, one of your speculations related to the actual interactions of the gases you have in the atmosphere. What would you expect to change if you played around with it a little bit? Do you have any feeling for this? If you would increase some of the ingredients in your test atmosphere? Or if you lower the for example, the aspect which did not quite match Mars today, do you have an idea if that would have an effect at all?
Yeah, well, I think if we would increase the oxygen concentration and we still keep on radiating the system, this will of course have an effect, I guess. Well, we are now working on a system to allow us to measure reactive gases. It's not easy to measure it because on the way to a measuring device they would react. So we have to measure them in a way remote. So with infrared sensing somehow, so that we can see that these gases actually form inside the chamber. And we are particularly interested whether they form close to the material, the biological material that we have inside our chamber.
Björn?
One factor was that some influence on this is that the sandstorm from Mars is moving matter around and eroding rocks and maybe exposing matter and then sort of cover over again. So this circulation of matter may mean that we have to dig much deeper than this kind of experiments would indicate.
So what we say is that...
Yeah, what I'm saying is that say that we from such experiments and these enhanced UV illumination feel that it's enough to dig a few decimeters. It may be failure just because it might have been exposed, let's say, 10,000 years ago and still quite well dead material.
I just wanted to ask, I'm not sure if I followed, but in your experiment, you don't add bugs or any of the organics.
No, it's just in the soil. We take what is there.
Okay.
Yeah.
So, have you studied some of the, the really dry, desiccation resistant guys that are also radiation resistant at all, like Dinococcus?
No, we have not in these experiments. But we have isolated organisms from the upper part.
Mm-hmm.
That's what we are doing now, just to do physiological studies with these organisms with respect to the different stresses that I mentioned.
So, are any of the best survivors? Since you said you did some phylogeny, is there any of the best survivors related to those that are already known to be desiccation resistant?
Yeah, well, a lot of them are actually actinobacteria, which are quite resistant to all kinds of. So they are known from these old permafrosts to be good survivors. And a lot of them are also pigmented, which may also be a hint. So they can somehow deal better with radiation and radical formation than others will. But it's just we started up these experiments now, so I cannot tell you very much. So just from a preliminary radiation experiments, they can survive for quite a long time. The problem is that they grow in clumps and colonies, and they don't grow as single cells. So you never know when you do survival experiments whether only one of these organisms survived in the clump or whether the whole clump survived. So they are, experimentally, they are difficult to deal with. But well, I think we can get around it and just start doing these experiments. Yeah.
Hey, René first.
Yeah, with regard to your question, I'm definitely not able to answer that. But maybe another useful approach would be to look into the survivability of the compounds in conditions which are not exactly the current ones, but the historic ones, where one assumed that maybe life was actually existing on Earth. Today, maybe we will just perhaps expect to find fossils or anything.
Yeah, well, I think the more you approach terrestrial conditions, the more sure you can be that there's no problem at all.
Okay.
You know, what you just if you just shield it a bit, you put a little bit of, let's say water, make energy sources available. Just what we know from microbiology of the Earth, we find bacteria in almost every habitat which just meets the most fundamental prerequisites. Not too hot, but up to about 100, let's say 20 degrees. Not too cold, but down to about minus 50 degrees. Find both organisms and activity, and it's not even needed to have sunlight. So we have organisms which just can thrive on chemicals like iron and nitrate, or sulfide and nitrate and iron, and so that's already we know this from this extremophiles studies of Earth. The question is now if on Mars, that's the tough question. If on Mars today you could find organisms, what we can explore is the surface, because we have a lot of information on the surface. Deeper down in Mars, where the temperatures are higher, where liquid water is present, that's a habitat which approaches much aquifers on Earth, where we know magmas can exist and live happily.
Christian?
The first table you showed, you had one column for the amount of amino acids bound in proteins.
Yeah.
Did I understand it correctly that on the deeper levels there were more amino acids in the test sample than in the control sample?
No, it was about the same. It was just in the upper 1.5 millimeter that we saw a reduction.
But I got the impression that it was significantly higher. Could I see that again?
This one?
Yeah. Okay, it's not significant.
No, it's just within the variation of the analysis.
Niels.
I was just wondering, is the permafrost soil the only substrate utilized so far?
Yeah.
So it's a very high organic soil then.
Yeah.
So we haven't tried to dilute it with something more Japanese.
No. Well, I think one of the experiments that we have planned is to use some kind of basaltic soil. Well, there are these Mars analog soils around that have been used for geological investigations. It's Martian soils of different kinds.
Did you have to get any results from it?
No. But what you can do, you can then just mix things into the soils and have a look how it will react.
Okay, interesting.
Alexis?
I don't know.
No, okay.
Alexis first.
Well, my question is related to your. I wonder how quickly do these guys move around? What is the migration faster?
With this systems, they don't migrate at all.
So millions of years.
Yeah, well, there's no water, so they cannot transport themselves. If they want to migrate, they have to move, and Well, the only way that they can migrate is when they get into some water, and then they can move in water veins as well. But in these systems, they cannot move. Or they can be transported. If there would be a dust storm in our system, then they could just be picked up by the wind and be blown to other places. But that's the only way they can migrate.
It's sometimes claimed that the condition for life on Earth is the magnetic field that to some extent screens the cosmic rays. And because on Mars there is no magnetic field, or very, very faint at it, and also the atmosphere nowadays is much thinner, so the load of charged particle is much worse. Do you think that the UV light is still the most dangerous component?
Well, the UV light is something that we can easily simulate in the lab. But of course, it would be very interesting to use other kinds of radiation and to see how this would affect the organism.
You could use asteroid maybe, right? The synchrotron.
Yeah, we could use this kind of light as well.
Samuel?
Remember correctly, you said that each sample was irradiated 3 hours.
Yeah.
And then 27 moved it, yeah. But have you tried to actually mimic the Martian day? How would that?
No, well, as I said in the first place, we just wanted to see if we could get any effect at all by the type of experiments that we were doing. The problem is with these kinds of experiments, this took us about a month, and you have to be present most of the time. You know, it's just like getting a baby. So and this is just from the tech.
So that's why you are inviting us.
Logistically, it's quite demanding. So after a month, when people were tired, then we decided to stop the experiment. But it would, of course, be very interesting to run it over a longer period of time and to run it also closer to the Martian conditions. But here, what we at least can see is that we can produce these effects, and we can also see that there are probably different kinds of effects depending on how deep we go into the system. And it also tells us that we actually, it's not necessary to go very deep before organic material is very well preserved.
I mean, how would it? Does some secondary heating play a role? I mean, the heating of the sample of your lab, of the soil sample.
It plays, of course, a role in the upper part, but not.
I mean, apart from the direct irradiation effect, I mean, it also heats the material, right?
Yeah, but only as long as it is exposed.
Yeah, that's what I'm. So that was why it must be interesting to look at all that change.
And of course, in our case, the heating was quite significant. I think the heating on Mars is maybe less compared to this situation.
Mats?
I was wondering, I mean, the atmosphere, coming back to the atmosphere, that I understand you can emulate by concerning the main constituents, but for example, free radicals, which plays a very important role in the troposphere, for example, for life. I mean, there could be extremely minute components that plays a very important role. Yeah. And how do you emulate that in your simulations? Yeah, well, the problem with the radicals is they by nature would react. Yes. Which whatever they came across. So I think it's difficult to. We can just we can create conditions which could favor the production of radicals, and somehow we do it because we have a little bit of water vapor, just water vapor coming from the steel, and the little bit of the small amount we can see in our experiment that when we cool, we actually have frost formation on the cool at the site where we introduce the liquid nitrogen for the cooling. So there is a slight temperature change while we cool. No, pressure change while we cool because there is some water vapor attaching to the mantle of the system. So there is actually water in the system, which then can be the source for radical formation. But we only think that this radical formation is of importance close to the material, the samples. And therefore, it would be very interesting if we could investigate it somehow, see whether it actually is formed or not.
All right, that was a really exciting session, and I thank all of you for listening, and thanks Kai for this talk.